listening to the Futures Podcast with me, Luke Robert Mason. On this episode, I speak with mathematician and science fiction author, Professor Ian Stewart.
Imagination is very important in mathematical research. If you just go down the obvious route using the obvious methods, either the problem's already been solved or everyone knows that doesn't work. The interesting problems are the ones where you have to find another way to sneak up on the thing. And I think reading science fiction books can help make you willing to try that.
Ian shared his strategies for explaining abstract mathematical concepts to the public, the role imagination can play in education, and how science fiction can assist in solving the world's most complex mysteries. I first met Professor Ian Stewart when he kindly agreed to speak at my 2011 revival of the University of Warwick's mid-90s cyberculture conference, Virtual Futures. He has dedicated his career to raising public awareness of mathematics, and I've always been in awe of his ability to take complex ideas and make them understandable to a general audience. He is a prolific author of popular non-fiction books, and in 1997 famously shared a stage with a live tiger as part of his Royal Institution Christmas lecture to demonstrate how symmetry occurs in nature. But what you may not know about Ian is that he has written several science fiction novels and short stories. During our conversation, he shared what sparked his love of sci-fi and how this led to him becoming a successful fiction author. He also shared a couple of anecdotes about his collaboration with fantasy author Terry Pratchett, which earned him the accolade of Wizard of the Unseen University. I had the privilege of recording this episode in person at the University of Warwick's podcast studio. As such, you can watch a full video version of this episode on YouTube by using the link in the description. Ian is a podcaster's dream. His depth of knowledge on his discipline is equalled by his boundless enthusiasm. I learned so much from Ian, not just about maths, but also about how to be a better communicator of complex concepts. It's why I'm so excited to be able to welcome Professor Ian Stewart to the Futures Podcast. Professor Ian Stewart, you're an emeritus professor here at the University of Warwick, and you're best known for furthering the public awareness of something called mathematics. And mathematics fills me with a lot of fear, but maybe we can talk about that in a second. But beyond your intellectual interests, you're also an accomplished science fiction author, and that's really what I want to talk to you about today. But I'm going to let you into that little secret. I've just hinted at it there. I'm awful at maths. I'm still awful at maths. Anything quant-based fills me with utter dread. And I just want to know, why is it that so many people are fearful of mathematics?
I think it's probably that the school experience is bad. If you have the sort of mind that can cope with it, relatively easily, then on the whole, you get most of the answers right. Yeah. There's a lot of emphasis on getting the answers right. If the answer's 5 and you've got 6, they don't say, well, that was close. They say, sorry, that's wrong. Yeah. And so there's nowhere to hide. I don't think it's the teacher's fault. I think it's just the subject is a bit like that. But I think a bad experience at school, you start to get scared of the next question, and the whole idea of it turns you off. Yeah, it was kind of opposite for me. But I did go through a bad experience when I was about 10, which my mother rescued me from.
Yeah, I was fascinated to hear that you originally were bad at maths. You were struggling at about 8 years old.
Yeah, well, I wasn't actually bad, but there were a series of events that made it look as if I was. So we were doing elementary arithmetic, and we moved on from addition to subtraction. But when the questions came up to write the answers, I didn't realise it was subtraction, so I added them all.
Right.
So I got every single one wrong. So that put me, we were streamed into something like 3 streams for maths. That put me down into stream 2, except 2 was split, and my surname begins with an S, which is way down the alphabet. Right. So I was down in group 3. And most of the other kids in group 3 were really, really bad. I just answered the question. I hadn't looked at the question properly. Yeah. Then I broke my collarbone.
Right.
And I was out of school for 5 weeks, and it was my right collarbone, and I write with that hand. So my mother decided it was time to sort out my maths. So she got the textbook from school, exercise book. I dictated everything to her so she could write it down.
Right.
And after we'd done 400 questions from the book, and I got 396 of them right, she went into the school waving this book and said, "There is absolutely nothing wrong with my child's maths." When I got back to school, I was about 10 weeks ahead of the rest of the class.
Right.
And they put me back up into the top group. And from that point on, it wasn't always plain sailing, but I didn't have any bad experiences with the subject. And I have that sort of mind. I really liked it.
Yeah. It's funny. You're basically saying that to just be good at maths, all I needed to do was break a bone.
That's it. In fact, it was a friend of mine. We were playing a game in the playground, and he pushed me over as part of the game. Right. And that was what broke the collarbone.
Well, do you think everybody has an innate mathematical ability? Is it simply something with regards to how they're educated that may turn them off or on from maths?
I think that probably, I wouldn't go quite that far, but most of us are much better at it than we think we are. It's very noticeable that young children, let's say 4 or 5 years old, are fascinated by numbers, by letters, by shapes, colours. This is the mathematical mind in action, and they really like it. And then they start to lose, most of them sort of lose that interest in these things. I think because it gets harder, because you're not just playing with coloured shapes anymore and solving little puzzles. You're actually having to do the technical, real stuff.
For me, I think it was always that process of abstraction, trying to get my brain to almost visualize what was being said about maths.
Visualizing is actually quite important for most people. There was a study done in the 1930s of how mathematicians think and how scientists think. And what emerged from that was that about 90% of them think in pictures, and the other 10% think in symbols.
Right.
So there was a biologist, a very famous biologist, who was asked, "When I say dog, what image appears in your mind?" And he said, "The letters D-O-G."
Wow. Okay.
And you think, what?
Yeah.
But even in very abstract areas of mathematical research, you'll see people talking. You go to the maths common room and see us sitting around chatting to each other, which is how maths actually gets done.
Right. Okay.
This is how you learn stuff.
That's the secret.
You talk to the expert over a cup of coffee, and in 10 minutes, the expert gives you an insight that you wouldn't have got in 3 hours of lectures.
Right.
But you'll see them doodling little diagrams.
Right.
We have blackboards, chalkboards on the walls. It's not because we're old-fashioned. It's because chalkboards, you can do a doodle and then you can scrub it out with your fingers and change it. You get covered in chalk, but you can sort of visualize what you're doing in much simpler terms than the actual technical thing it turns into. By the time you've published it, most of these diagrams have disappeared. But they give you a way of, the human visual sense is very, very powerful. So if you can co-opt that to help with your maths, then you've suddenly got a really powerful tool which makes things a lot easier. It's hard to teach that because if you start teaching it to people, then as well as the maths, they've now got these funny diagrams and the link between them. Right. And this is more stuff to learn. So it doesn't always work like that. But if they can invent this way of thinking for themselves, then you make the subject, you make it your own. You personalise it.
What is it that mathematicians see in their head when they're visualizing these things? Because we see these representations in film of the falling equations and all the letters swirling in films like Beautiful Mind. Is it like that, or is that an unfair representation of sort of how mathematics is done in someone's head?
It's not a bad one. If you look at the notebooks I'm carrying around at the moment, because I've been working on various problems for quite a while, some related to research, some related to a new edition of a textbook, it's full of stuff that looks rather like what you see in the movies.
Right.
There's scribbles, there's stuff crossed out. It's not organised.
Right.
It's extraordinarily disorganised, because when you're coming to grips with a bit of maths that you've not seen before, it gets very confusing. However good you are, it gets confusing. You think, it doesn't make sense. What's going on here? No, but surely that can't be true, because and then after a while, when you mess around like that, a little light bulb goes off. Say, I see what I'm getting wrong. Right. I'm not thinking about this the right way. Good friend of mine, many years ago, I did some research with him and wrote a textbook with him, Tim Poston. Right. He went to a course on topology. Rubber sheet geometry, they say. The donut is the same as a coffee cup, that stuff. Okay. Only this was high-dimensional topology. And he went through an entire MSc level course on this, and he said, didn't understand a word of it.
Right.
And about 2 years later, suddenly he thought, oh my Lord, I misunderstood the basic definition of all the concepts that were being used.
Right.
So the whole picture in my head was wrong. And he was a very visual thinker. He made mathematical sculptures and all sorts of things. Wow. But he had the wrong picture in his head, so it didn't make sense. And then suddenly the subconscious, I think probably somewhere in his brain, something was working on this. And it wakes you up and says, it's almost as if your brain taps you on the shoulder and says, hey, by the way, have you thought of this?
Does most maths actually occur in the subconscious? Does most of those sparks of inspiration that artists describe, does that happen for mathematicians too?
Yeah, I think so. There's a very famous article by Henri Poincaré, who was probably one of the 2 or 3 leading mathematicians in the world at around 1900. And he described what it seemed like when he was trying to solve problems. And he said, firstly, you have to get started. You just have to work on the thing. You work really, really hard and nothing makes sense. And then you go away and stop thinking about it. And you work on something else or whatever. And on one occasion, he was working on a very difficult problem, and he'd done all this. He'd done the sort of incubation period, and then he just relaxed and forgot about it. And he was getting onto a bus, and suddenly the light bulb went off. Oh, now I see it all.
Right.
And everything clicks together. And one of the wonderful things in math research, you spend 99% of your time banging your head against the brick wall. And the other 1%, suddenly, it's not just that you solve a little bit of the problem, but it's as if the whole thing clicks into place.
Yeah.
It all begins to make sense. And a whole pile of other stuff suddenly comes very easily. And you get this great rush of, wow, hey, I've understood it.
well, the things you work on, they're such complex problems. To someone who's not maths proficient, they feel very complex. But as a science communicator, as a mathematics communicator, how do you make these complex ideas understandable to the general public?
There's usually some sort of story behind it, right. And you can tell the story. And because you're not writing a paper for a journal or writing a textbook, you can be fairly freewheeling about how you describe things. Right. For example, part of my research for a long time, I still do bits of it. In fact, I'm writing a paper on it at the moment. Technically is about the effects of symmetry on dynamical systems. Right. So all sounds technical. So symmetry we sort of understand. Dynamical systems, something that evolves over time according to fixed rules, right. Like motion of planets in the solar system, or the legs of an animal. Right? Now, animals move in interesting patterns. If you look at an elephant walking, as one does from time to time, and you look at which feet hit the ground, you find it goes left rear, left front, right rear, right front, left rear, left front, right rear, right front. Right. You can hear the rhythms. It's quite musical. And they're evenly spaced footfalls, unless it stops to look at something interesting or whatever. Right. So if you look at a dog moving very fast, the back legs go, then the front legs go. back legs together, front legs together. It's like you see it in cartoons particularly. Right. If you look at a horse trotting, diagonally opposite pairs hit the ground together and alternate. After you've studied this for a while, you can look at an animal moving and say, oh, yes, rotary gallop. I do this all the time with the wildlife programs on television. And my wife's doing it now, and she's not at all mathematical.
Well,
but she looks and says, oh, yeah, I recognise that one.
I bet you're fun at the zoo.
Some people feel this spoils the experience, but actually I find it makes it more interesting.
Right.
You notice things. Yeah. But so I can explain the kind of research I was doing in symmetric dynamical systems by talking about animals moving. Right. And in fact, I've given that talk to colloquium talk to professional mathematicians, talk to kids in schools, talk to a science fiction convention, and with very little tweaking, it's the same talk.
Well, that's convenient. But that's one of the things I'm fascinated by with your work. You use biological concepts to explain maths and use maths to explain biology. So how do those two fit together?
This is... I didn't start out that way, right. But I've always been a bit of a butterfly brain. That is, I do sort of flit from one thing to another. Right. But if you flit from enough things, you start to notice connections. And in fact, I got into this business of animal movement. I was doing the abstract mathematics of symmetric dynamical systems. Right. And New Scientist sent me a book to review, which was a book by engineers. It was a collection of short papers on engineers taking inspiration from the natural world. Right. And there was one, they were interested in making robots walk, or robots with legs and 4 legs, 6 legs, whatever. Uh-huh. You have a robot with 25 legs if you want. And somebody had written a paper about the natural patterns of animal movement, right, and applications to robotics. And I looked at this and thought, I've seen those patterns that they're talking about, and they're in my symmetric dynamical systems. Right. It's the same patterns. There must be a link. And I mentioned this in one sentence in the review. Right. 2 days later, I got a phone call from an American in Oxford saying, I'm a biophysicist. I work on animal movement, among other things. That's fascinating. Can we talk? Wow. His name was Jim Collins. He's now very famous. And he got one of these MacArthur Genius Awards that the Americans give people. And so there was a contact with the biology, and we wrote 6 papers together, ultimately, and dragged in various other collaborators. So there are these connections between patterns in the biological world and mathematical patterns. And for a long time, a lot of biologists kind of resisted this idea. Right. That wasn't biology. They didn't, and of course, the mathematicians didn't understand the biology, so they made all sorts of silly mistakes. Right. And biology is very, very complicated, so maths is too simple. Well, hang on, you're doing biology because maths wasn't too simple. But it's much better now. There are lots and lots of collaborations between mathematicians and biologists. I'm currently working mainly over Zoom with some physicists in New York who also work with biologists, and we're looking at the effects of symmetries of a more general kind in genetic networks and in networks of nerve cells in animals in the brain, right, particularly. And there's lots of mathematical structures, mathematical patterns, and new techniques where maybe the biology has actually stimulated the mathematicians to think about something new, and then you can feed it back into the biology. So increasingly, this is becoming a fairly natural activity.
Well, that word "natural" I want to draw on, because it feels like one of those great philosophical questions: is maths present within nature, and maths came before nature, or nature came before the maths? Because those two seem to so seamlessly fit together as a way of understanding reality, and I've never quite understood how that occurs.
Yeah, I don't think anyone can claim. Well, if they do claim to understand it, my feeling is probably they don't, because there are some easy explanations like the world is built out of mathematics.
Yeah,
I don't believe that
before.
one.
Right, okay,
I just don't believe it, no. But somewhere deep down, the world seems to be more, the deeper you look into the atomic structure and molecular structure and then quantum mechanics and things like this, and it just gets more and more and more mathematical. Yeah. My feeling is that the mathematics is the way our brains come to terms with trying to understand that stuff.
Right.
But I did write a book with a friend called Jack Cohen with the title Figments of Reality. So this was the converse of reality being a figment of our imagination. We said, no, our imagination is a figment of reality because our imagination works in a real brain, which is, made from nerve cells and other stuff. And if there weren't some sort of regular structures in the real world, our brains wouldn't be able to function. Yeah. And they said, how can we understand mathematics with this gadget if there's nothing mathematical floating around? Yeah. It seemed very strange. So you can kind of argue it in several ways. So my feeling is a lot of the universe seems to be mathematical. And the more maths we understand, the more true that seems to be. On the other hand, a lot of our maths is abstracted from the real world in the first place.
Right.
Not all of it. And this is where so some of it just seems to be inventions of the human mind. Yeah. The whole of number theory, which is all to do with prime factors and all of that stuff. Very few things in nature work with prime factors. Right. Even the ones that are sometimes mentioned seem rather artificial. But we're fascinated. Certain people are fascinated by this stuff. And this has been going on for years and years and years. And a whole pile of mathematicians have been developing number theory with no particular application in mind. And it's now fundamental to internet security. Right. Because the secret codes that are used on the internet, the crypto systems, some of the most important ones are based on number theory. They're based on things that were discovered about 300 years ago. Yeah. So there's this funny interplay between the stuff that the human mind seems to invent for the fun of it, the stuff that we abstract from nature because Isaac Newton, trying to understand the motion of the planets, comes up with a mathematical scheme, calculus, to solve it. And then the miracle, you start putting those together, and some of the stuff you abstracted from one aspect of nature suddenly illuminates a totally different one. Yeah. So Isaac Newton's differential equations now tell us about how epidemics spread, how animals move, a whole pile of things that have nothing whatever to do with what motivated him to develop it in the first place. Wow. Yeah? Yeah. The standard phrase for this is the unreasonable effectiveness of mathematics. Unreasonable effectiveness. And the important word here is not effectiveness, it's unreasonable.
Yeah, I thought mathematicians were unreasonable.
Yeah.
That's something we both can agree on.
It works even when it shouldn't.
Yeah, that's what always confused me about maths.
Yeah.
Like, why does it
work? Yeah.
Yeah, it is one of those weird things. But you've used a multitude of ways to explain these things that just seem to work. You've used puzzles, you used games in some of your books, you've even used tigers. So what are some of the tools that someone can use to explain these complex concepts?
Okay, some of these concepts are really, really difficult, and what happens is that the popularisers shy away from them. Right. I wrote one book, 17 Equations That Changed the World, and had to come to grips with some of the technicalities. And there was another book where I was going through some of the big unsolved problems in mathematics, and several of those are very, very technical. Mm. And one chapter I say at the beginning, I'm going to have to do this. I can't leave it out. Uh-huh. It's really hard even for me. Right. How can we explain this? And I'm actually trying to explain what technically are called cohomology groups in algebraic topology.
Okay, you've completely lost me.
Okay. And the way I start to explain it involves sticking labels on cows and sheep and other things. Right. Because in cohomology, It's like trying to add 3 cows to 5 sheep. Okay, you can imagine that. Have 3 cows in a field, bring in 5 sheep. What about 3 cows plus pi times sheep? You want 3.14159 sheep. How do you do this?
Right. What the funny thing is, my head went apple pie or rhubarb pie.
No, yeah. Circle pie.
Circle pie. Yeah, okay, here we go.
Okay, right. Okay. The trick, and this is what the algebraic topologists do, you slap a label on the cow which says 5.
Right.
And you slap a label on the sheep that says pi. And then if I want to add labelled cows and sheep, I just add the labels.
Right, okay.
5 cows plus 3.5 cows. I don't need 3.5 cows. I need 1 cow with a 5 on it, 1 cow with a 3.5 on it. And when I add them together, miraculously, one of the cows disappears and the numbers add up.
Okay.
And this is how cohomology works. Okay. So this is now all great fun.
Yeah.
Whether we've understood anything about this particular area of mathematics is another matter altogether.
Wow.
But you can sometimes torture the mathematics into sounding friendly,
right,
even when really it's not.
Yeah.
But most of the time, if you're sensible, you select topics that have some sort of story behind them that can be explained.
Yeah.
And then the trick is to find the best, find a way, there isn't a best way, to find a way to explain this.
Right.
Now, when I was doing the Christmas lectures on television, this is the tiger story. Well, the 5th lecture was about symmetry. It included the stuff on animal movement that I talked about. And we illustrated that by dressing 2 kids up in a pantomime camel come pantomime elephant,
right,
pantomime horse, and getting them to move their legs in the relevant patterns,
right,
which was highly amusing. But I wanted to start with the William Blake Fearful Symmetry quote, "Tiger, tiger, burning bright." Well, television being television, if you start talking about tigers, you've got to have one.
Tiger.
You need a tiger. And my friend Jack, biologist friend, spent 6 months hunting for tigers that were media friendly.
Right.
And 2 weeks before we were due to film, he found one, which was 6-month-old tigress called Nika,
right,
who had been round schools and been shown to school children.
And hadn't eaten anybody.
Hadn't eaten anybody,
Okay.
was very well behaved. Yep. And so we duly they tipped the front seats in the lecture room up to make a barrier between the audience, which was 500 kids, and the tiger. The tiger had 2 burly young men holding onto it by a chain.
Right.
And nothing to protect me.
Yeah. Okay. I have seen the clip. Yeah.
I interacted with the tiger. She was lovely.
Yeah.
I mean, I like cats, and it was a very well-behaved tiger. And the point actually was not just the metaphorical symmetry, but if you look at the tail of the tiger, you see very regularly spaced stripes.
Right.
And there is a mathematical theory of pattern formation in animal markings,
right,
which goes back to Alan Turing, who is best known for his decoding of the Enigma machine at Bletchley Park during World War II. Turing came up with a theory in the 1950s about animal markings,
right,
which was quite interesting to the biologists to begin with. Then they went off it for various sensible reasons. It didn't explain everything they wanted. It's coming back into use again because modern experiments can delve into things a little more deeply. And the reality matches the mathematics better than people thought. Anyway, so I could talk about the stripes on the tiger, and there are computer models which have animal-shaped surfaces and do Turing's equations on these surfaces, and you look at the tail, and lo and behold, you get stripes.
Wow. Okay.
So so this is where the tiger came from.
Is that? You're saying we're finding out more. Is that genetics? Or
Yes, it's mostly the genetics. Okay. The big flaw in Turing's theory when he first proposed it was he hypothesized that there are various chemicals in the developing embryo which must interact in certain mathematical ways and create the patterns. But he didn't say what those chemicals were. and nobody knew what they were. So they were this kind of invisible assumption. And it was sort of reasonable. There must be something like that. But now they know what they are.
Yeah.
They can actually tell you what the molecule is. They can tell you how it behaves. They can watch it interacting. They can see the waves moving according to Turing's equations. There's some lovely work on stripes on angelfish where the stripes move slowly.
Oh.
Over a period of about 6 to 12 weeks, stripes on some angelfish move.
Oh, I wasn't aware.
They're a bit like stripes on a barber's pole moving when the pole revolves, the spirals, but very, very, very slowly.
Is it an optical illusion, or are they actually?
They are actually moving. If you made the right sort of slow motion film of the fish, which would be hard, you have to hold it still for 12. You put it in the same place and you photograph it repeatedly. You would actually see the movement.
Wow.
And this is predicted by Turing's equations. So, this is fascinating stuff. Yeah. Now, with stories like that floating around, the key thing is to spot the stories.
Spot the stories.
And then you structure your book or your magazine article or whatever it is around these stories.
Yeah, that's fascinating. I was going to ask about one of your recent books, What the Use. You explore the practical applications of mathematics using some of those stories, because it's all well and good to know this stuff, but how it appears in the real world, how it affects our everyday lives is so important too.
That's right. And of course, the problem for mathematicians particularly is nearly all of that stuff is completely hidden. And you take out your mobile phone and say, where's the mathematics in that?
Yeah.
Well, everywhere. Right. It just would not work without it. Practically everything it does, there are hundreds and hundreds of mathematical algorithms which, you've got to get the picture on the screen. How do you do that? Well, it's encoded in numbers. How do you go from the numbers to the pictures? Yeah. How do you actually cram all of this stuff into it, even without thinking about making one? And it talks to the internet over the phone lines. Yeah. How come? How does it do that? It's got a camera. How does the camera work? Optics, the lenses in the camera, it's extraordinarily mathematical designing these things, because you've got this tiny little lens which is giving you HD quality video on your phone.
But it just works.
The mathematicians are the magicians. Well, the engineers applying the mathematics, the physicists who devise the theories, a whole pile of other sciences come in. Right. But embedded in this, right at the root, is enormous amounts of mathematics. So I wanted to write a book that kind of opened that up to people, because most of us, you don't see it. You go through school, you do maths in school, you say, well, it might be useful for a few things, but I'm glad I don't have to do any more of that.
Yep.
And then you get into the frame of mind, why do we have mathematicians anyway? Can't computers do it all? And, what's it for? I thought, well, that's a good question. What's it for? Yeah. So the point of that book was actually to take surprising applications of areas of mathematics you probably never even heard of. Right. So both the mathematics and the application should be surprising. And then the link between them should not be straightforward, this maths was devised to answer this question. Right. The link should be, this maths was devised for a totally different reason. Lo and behold, 300 years later or whatever.
We found an application.
Yeah. So one example quickly was there's an ancient puzzle of the bridges of Königsberg, where there are 7 bridges in the city, and the question is whether you can go for a walk and cross each bridge exactly once. And they're linked together. They link 2 banks of the river and 2 islands, so it's a complicated arrangement of bridges. And nobody could find a way to find a walk like this. At some point, you have to go over another bridge twice. Right. Okay. I mean, you can imagine if one bridge led to an island, there's nothing else there, you'd have to turn around and go back again. Okay. But there's always another exit. But the way the bridges fit together actually stops such a walk being possible. Right. Now, Leonhard Euler, who was the great mathematician of the period, wrote a little paper proving that it's impossible. And this kicked off an area known as graph theory. Right. Which is about dots connected by lines. One of the applications of graph theory is making kidney transplants more efficient.
Wait, what? So
Kidney transplant.
How do we go from bridges to kidneys?
Exactly.
Ian?
Okay. So essentially the analog here is in a kidney transplant, you have two people, donor and recipient. Somebody gives a kidney, somebody receives it.
Right.
Okay. Now, matching them up with the right tissue types can be very difficult. But somebody had a bright idea. Yeah. And basically, people normally, there are a few altruists who are willing to donate one of their kidneys to anybody. But most people say, if it's my brother or my father or my mother or somebody, a close relative, or even perhaps a very good friend of mine, I'm willing to donate, but I won't donate if it's not.
Right.
But particularly, the tissue types don't always match. But suppose you get two pairs of recipients and donors where if one of them, instead of donating to his brother, donated to the other person, and the one who was going to donate to the other person donates to his brother, so you swap donations, you can put the two together and say, your kidney donation indirectly will be a kidney for your brother.
Right.
And this works with both of them. So these kidney swaps make the whole thing much easier to arrange.
Right.
Okay. Now, there's a little graph attached to that, which is the first donor and recipient pair is one island.
Right.
The other pair is the other island, and the bridge between them is the swap.
Right. Okay.
Well, now you can start thinking, hang on, we don't just have to have two islands and one bridge here. You could have 7 pairs connected in some way with the bridge works if the swap matches the tissue types.
Right.
So you can draw a network of donor-recipient pairs and possible swaps and start saying, is there a threefold swap? Could there be more? And then even more people can get kidneys.
And everybody's indirectly
Everyone's
benefiting.
indirectly linked.
Right.
And now you are using quite powerful computer algorithms to find the most efficient way of matching donors to recipients based on this graph theory stuff. And this is used by the NHS. This is really used.
Right.
And the mathematics of the algorithms, these are very big graphs. You have thousands of people. So finding the most efficient way to break the graph up into little cycles where everyone could swap is a very difficult mathematical task. But the computer algorithms are up to scratch on solving it. And this is how it's done.
Yeah, you keep mentioning this idea of computer algorithms and the idea that maybe we don't need humans in the loop to do mathematics, and this idea that AI can start solving these complex mathematical equations and we won't need mathematicians. I mean, you start to believe that's true, and then you suddenly realize that the AI requires maths to work anyway. So
that's right. I mean, it could go the way of some of the science fiction novels where the AI gets so smart that it doesn't need us anymore.
Right.
Yes. Yeah. And I don't think that's impossible.
Right.
I don't think we've reached it yet. But without the mathematics and a whole pile of things, computer scientists who are very good at thinking about structuring mathematics into algorithms. Right. It's not enough to know the maths. Have to put it together in a way a computer can do.
Yeah.
And of course, the amazing physics and engineering that goes into building the computers. There's all of that. But at the heart of these algorithms are mathematical ideas. And the whole of artificial intelligence is actually mathematics applied on, it's actually fairly simple mathematics.
Right.
Undergraduate level is fine.
Yeah.
It's the way you use it. And they've got very good at finding out how to actually construct the right kind of mathematical structures that can learn things effectively. I mean, whether our brains do it the same way is not at all clear.
Right.
But these systems learn.
Yeah.
And they prove they learn because they can answer questions and they can talk to you and they can translate between languages, and they're certainly getting very, very powerful.
But they're not going to replace mathmaticians anytime soon.
Not yet.
Let's hope not. One of your books, which I love the title of because there seems to be a juxtaposition of terms there, is Infinity, a very short introduction, which how do you do infinity in such a short little book? But it's one of those beautiful little Oxford, very short introduction books. Infinity is such a complex topic. What made you want to write a short introduction to it?
Okay, I was invited, that series, everyone who writes those books are invited to do so by the editors at Oxford University Press. You don't send a proposal to them.
Oh, I see.
You wait until they contact you. Of course, it helps if you've had contact with them in other ways. I have several books through OUP. So I was kind of on their list. And the editor sort of sent an email, I think, and said, we're thinking a book on infinity might be quite a nice idea. And we both appreciated this juxtaposition of words.
Yeah.
Would you like to write one for us? And she explained to me the kind of description of what they wanted. And for that series, they don't want the bog standard textbook approach to the topic. Mm-hmm. They want something slightly quirky, but not too quirky, which puts over important parts of the subject area in some way. So basically, I thought, well, I'd love to write one of those. They're such nice little books. I mean, whenever anyone says write a book, my ears prick up and start to get excited. In fact, one of my publishers said I was writing too many books and I had to slow down because they trip over each other unless you're careful. Okay. This is actually why I write science fiction novels, because they don't trip over the maths. I can do those simultaneously. And if I publish one of, a science fiction novel, it doesn't do anything nasty to the sales of the maths books.
Right, okay.
And conversely, you see, they don't.
It's the sales numbers they're worried about. Those are the mathematics they're worried about.
This is what the publishers are worried about.
Okay.
Yeah, that's their business.
Yeah.
I'm more interested in people reading them.
Right.
But it's nice to have sales. It's nice to have money coming in. Terry Pratchett always said he didn't object to the money. But writers write because they want to write.
Yeah.
Anyway, so I essentially sat down and thought, well, what are the interesting stories about infinity? Can we make this as broad as possible? I could spend the whole book talking about mathematics of infinity, but it comes up in philosophy, it comes up in theology. I'm an atheist, but it's still, theology is sort of interesting in certain ways. Yeah. So it comes up geometrically in the theory of perspective. There is a line at infinity, the horizon.
Right. In
the geometry of perspective, there is a meaningful sense in which that really is at infinity. Because if the Earth were flat like a Euclidean plane, the horizon is not part of the plane. It's infinitely far away.
Right.
Yeah. It's where the plane seems to stop when you look at it horizontally.
Right.
But your horizontal line is parallel to the plane. It never actually meets it.
Right.
It just looks like it. Why do railway lines appear to converge when you stand in the middle of the track and look down before the train comes? Because of what's called projective geometry, which has the whole idea of a line at infinity.
Right, okay.
So very rapidly realised there are about 6 or 7 topics that I could talk about. What about real infinities in physics? Is there anything genuinely infinite in the universe? Good question. Some people think the universe itself is infinite.
Yeah.
It may be the only thing that is.
It is. Yeah, there we go. You hinted at it there. You've written 120 books, I think, is what's been quoted online, or over 120.
Yeah, around about that.
Books. How do you do something like that? How do you achieve that much output in an academic life?
Well, okay. I mean, I'm 78.
Right.
This helps.
Yeah, but that's almost 2 books.
2 books a year is kind of what it works out as.
Yeah.
And if you can write a book in 6 months, which I usually can,
wow, you
can do 2 books a year. And I don't spend the whole time working on the book.
Yeah.
In fact, I tend to overlap them. I tend to it's not a linear process at all. The main thing is there's usually a deadline, and if there's a deadline, I pride myself in meeting deadlines.
Right.
And the closer the deadline gets, the more attention that book gets.
It's weird that.
I have occasionally missed deadlines, usually by 20 or 30 years.
Okay.
The book gets shelved and then much, much later gets revived. So this does happen occasionally. I think twice this has happened to me.
Right.
Now, quite a chunk of those 120 were how to program your ZX81 home computer and things like that, which I wrote with a friend. And there were a whole pile of different makes of home computers coming on the market. And when the new one came out, BBC, the Warwick and whatever, we would rewrite the books. We had 3 or 4 books for the ZX81. We'd rewrite them all again for the next one. So technically these are different books.
Right.
So if that would reduce the number to somewhere in about the 80s if you don't allow them. But I've done undergraduate textbooks. I've done research texts. I've done 2 children's books, technical books, popular science is the main category, and increasingly science fiction books.
Yeah. Well, I wanted to talk to you about your science fiction work. I was so surprised because secretly I have this collection that I've been collating over the last decade of Omni magazine, of Analog magazine, of Future magazine.
Right.
Because I discovered on eBay you could just pick up these boxes and boxes. I've got a storage unit full of these things now. But these pulp science fiction stories.
Oh, yes.
And they're fantastic. Some of them not so much, but the majority of these short stories are fascinating. And we don't encounter science fiction in that way anymore. There's shows like Black Mirror on Netflix, and there's new popular media and new ways in which people engage with science fiction. But the process of writing a story is still so fascinating to me. And I found out that your journey began with Analog magazine.
It did indeed.
Yeah.
Yes. I mean, I'd been a science fiction reader, books and magazines, from about the age of 14.
Right.
But in 1977, my wife and I and our 2 kids went to the University of Connecticut.
Right.
Storrs, Connecticut, which was a former agricultural college. It still had cows. It had a fantastic ice cream parlour. They made their own ice cream from their own milk. It was out in the wilds from nowhere. The town was the university.
Right.
But the big town in Connecticut was Hartford.
Right.
And Hartford, Connecticut, about 30 miles away, was where Ben Bover, the editor of Analog magazine, lived. And I'd written a popular science article with my friend Tim for Analog magazine about applications of topology, actually, because they had a science facts section. And so Ben invited us over for the evening. So the whole family went over to Hartford, and he said, somewhere in the middle of it, he said, why don't you try writing science fiction stories? So I thought, well, that's an interesting idea. Yes, it quite appeals to me. But I didn't have much of an idea what to write.
Right.
A few months later, my wife came home. We were heading towards the winter, and winter in Connecticut is 2 or 3 feet of snow, and on the whole, you don't go anywhere much. And we were stuck in these university apartments. And she came home with a box from the flea market and dumped it on the table and said, this is something for you to do.
Right.
And I looked in the box, and it was pieces of a typewriter, about a 1920s typewriter.
Oh, wow.
I actually recognised the typewriter because my dad gave me one from he found in the bank where he worked when I was younger.
Right.
So it was a familiar model. And so I started cleaning it up, putting it together, sort of repair shop style, and all the pieces were there.
Wow.
Even a ribbon, put it together, it worked. Thought, well, I've got a typewriter, I better write something on it. What can I write? Oh, science fiction novel, story, short story. And I had an idea for the story, so I sat down and worked it out and typed it and sent it to Ben Bover and said, okay, tell me what's wrong with this and I'll rewrite it.
Right.
Next thing I knew, there was a letter from him with a check. He bought it.
Right. Wow.
And it appeared in Analog. It took me about 4 more attempts before another one appeared in Analog.
Okay. I was about to say you're annoying all of our science fiction writer listeners.
That's right.
How
you just
quickly.
get lucky.
Okay, it was luck.
It was luck, and then after that, you had to work for it.
Right.
Yeah. And I did a trickle of short stories over the years, mostly for Analog or Omni.
Yeah.
And then quite a bit later on started doing some novels.
Right.
And the first novels there were actually with my friend Jack Cohen, the biologist.
Yeah.
Jack was a science fiction fan. He was the kind who went to all the conventions. He was a convention animal. I was the kind who collected all the books and magazines.
Yeah.
Our house has something like 8,500 of them.
Wow. Wow. Well, if you need a storage unit.
My wife tolerates this. So Jack and I got together and we did various things. We wrote several popular science books together, and we collaborated with Terry Pratchett, thanks to Jack.
Of course. Yeah.
But we wrote a couple of science fiction novels, which were published by one of the big American publishers. We did quite well at that point. Then I did a couple with my friend Tim, one of which we had designed 30 years earlier but never finished writing, which we finished.
Right.
And then Tim thought of a wonderful sequel to it, which we wrote in 6 months.
Right. As you do, yeah.
And from time to time now I produce another science fiction novel or short story collection, culminating in the latest one.
Yeah, Loophole.
Yeah.
Which is about two universes meeting. And I want to discuss a little bit about Loophole, because how do you get to these concepts? I once interviewed Warren Ellis, who told me the question you never ask science fiction authors is, where do you get your ideas from? But in your case, you're really fascinated by the hard science fiction, the science behind how these worlds work.
To some extent, but there are several things in that book that are definitely not consistent with current science. It's in the details a little bit.
Right.
This is what Brian Aldiss, a great British science fiction writer, called space opera.
Right.
And it's also called widescreen baroque.
Right. Okay.
So this is the far future big concept, worlds colliding, universes colliding, vast spaceships, all of this sort of stuff.
Yeah.
Which I rather like. But with you pay lip service to the science.
Yep.
If you're going to have faster than light travel, which the story won't work without it, basically. Right. This particular book begins with a voyage to a star 30,000 light years away.
Yeah.
Well, you've got to move the story along. They've got to get. It takes them 6 weeks to get there.
Yeah. Only 6 weeks.
Only 6 weeks. Yeah, because their spaceship's not one of the most powerful ones, which would do it even more quickly.
Of course.
But they get there. So you pay lip service to it by inventing some sort of way to get round the speed of light limit in relativity.
Yeah.
And in that book, that they use a thing called a metasphere.
Yeah.
The metasphere is a baby universe, which is surrounded by our universe. It's like a little bubble, but actually it's detached from our universe by an interface.
Yeah.
And it is good physics to say that according to general relativity equations, although matter cannot move faster than light, bits of space can.
Right. So move the space,
move the space with a spaceship inside it. As far as the spaceship is concerned, it's not going anywhere.
Yeah.
It's just sitting at the centre of its metasphere. How do you generate the abscission engines will do that.
Oh, okay. There's the science fiction author license.
Yeah. So suddenly the science has escaped, but you've at least acknowledged that you know that these things are not completely possible yet, but they might be.
Right.
Yeah.
Well, did you always have a love of science fiction? I know you were creating star maps as a child.
Oh, that's right. Yes. Yeah. It was Dan Dare in the Eagle comic. Yeah. So my mother wouldn't buy me the Beano or the Dandy because they were she didn't think they were intellectual enough.
Right, okay.
But she would buy me Eagle, which the Eagle was renowned for being the kind of the comic for the I mean, we were working class, but my mother wanted it to be educational.
Right.
So she wasn't going to spend money on a comic unless it was educational.
Right.
But right on the front page of the Eagle magazine, in colour, were the adventures of Dan Dare, pilot of the future. And I also listened to, they had an old radio, which I had in my room, and I could listen to the radio in the evenings, maybe for an hour or so after I'd gone to bed. Radio Luxembourg 208 meters had a Dan Dare serial.
Really?
Yeah.
Oh, wow, I didn't realise.
So I listened to that. Yeah. And so I grew up with that sort of stuff. And so moving to reading Arthur C. Clarke or Asimov or Heinlein or other of the science fiction writers of the 40s and 50s was very natural. I discovered the local second-hand bookshop had lots and lots of El Cheapo science fiction books, all of which I still have.
Right, yeah. The pulp collection.
Oh, yeah. So that's how I got into reading it. A friend of mine was also very keen on the same thing, and we had a sort of competition for who could have the biggest collection.
Right, yeah.
And for a long time he won. Yeah. He cheated. He went to London University and there were lots of really good second-hand bookshops in London, which I couldn't get to. I think by now I've caught up and overtaken.
Right, okay. And your wife wants to pulp all of them. Well, I do want to ask, this love of science fiction, I hadn't realised it was so early on in your life, but do you think having had science fiction influence you as a child, do you think that has appeared in the way in which you do mathematics?
I think so. I think it, I'm sure this doesn't work for everybody, but I think it broadens your imagination. Yeah. It lets you, I mean, imagination is very important in mathematical research. If you just go down the obvious route using the obvious methods, either the problem's already been solved or everyone knows that doesn't work.
Right.
The interesting problems are the ones where, you have to find another way to sneak up on the thing. And you've got to have this kind of willingness to throw away the conventional wisdom and try something different. Right. And I think reading science fiction books can help at least make you willing to try that.
Yeah, or at least stimulate the imagination.
Stimulate the imagination. It depends. There's good science fiction. There's bad science fiction. You mentioned this. Some of the stories in the pulp magazines are pretty rubbish. Yeah. But there's some good stuff there. Yeah. There's some good, even if it's not very literary. The story really travels. They tell a story. I think the literati don't quite understand that even if something is beautifully written with wonderful English, if actually it gets rather boring when you read it, is this worth doing? I mean, it probably is worth doing, but it's not the be-all and end-all. And we, the authors of the airport books that you buy and lug with you on the plane, or these days download to your Kindle because it's a lot less to carry. My wife and I used to travel with about 20 books to read. Wow. Now we travel with 2 Kindles. It's much better. So, but the authors of those books, Lee Child, Jack Reacher's stories, there are various features of that that's totally unbelievable, but by God, they travel. And other authors of that kind. They know how to tell a gripping story. And so did the pulp writers of the 1930s and later.
Are you able to read a science fiction novel or a science fiction short story without looking at it and trying to see if there's possible mathematical problems? I hinted at it earlier, this idea that you read Dan Dare but ended up using that material to create a space map, a star map.
Occasionally I find I'm reading the book and suddenly there is something in it that does not fit with what I know about science and mathematics. Right. I won't name the author or the story, but there's one book where the aliens come in and heat up the atmosphere of a planet. And, of course, hot air rises. So the entire atmosphere rises off the ground level, and everyone on it dies from asphyxiation because there's no atmosphere. Right. The problem is it wouldn't work because hot air rises because cold air comes in underneath to displace it. It doesn't just rise of its own accord. And the whole series is structured around this technique for aliens taking over planets by killing everybody off. And it simply doesn't work.
Well, is there any science fiction work that you've read that's maybe inspired your mathematical inquiry or mathematical research? Or equally, is there any science fiction out there that you've seen or read recently that really gets the maths right?
There are certainly ones that really get the maths right. I mean, even if you go back to Isaac Asimov's Foundation series with psychohistory, which was a mathematical technique for predicting the future, he says explicitly, look, you can't predict the actions of individuals, but you may be able to predict how society en masse will change. And it's a very famous classic trilogy, whereby book 2, everything that's set up in book 1 isn't working properly anymore. And in book 3, you discover they thought of that as well. They knew that was going to happen. They predicted that. They predicted that their method for predicting the future would cease to predict the future. So they had a plan B set up.
As you do.
Isaac Asimov was very, very clever. Yes. Stephen Baxter, who's a good friend of mine, actually. Stephen writes fantastic far future. He writes several kinds of things, but one of the types of book he writes he has this whole series of ever further into the future events based around frontier physics research. So there are things living in the sun which are made out of abnormal matter, supersymmetric particles, things like that. And he tells very gripping stories feeding in this frontier physics, so frontier that it's theoretical, it's not even known to be practically true, but it's the front, there's the whole frontiers of particle physics are speculations about what the next theory ought to look like, rather than working out what the current theory does. And his books it's very cleverly done. It's not obtrusive, but there are aspects of this fundamental physics that are underpinning the entire structure of everything he writes there.
Well, for you personally, does it start with a creative idea, or does it start with perhaps a scientific or mathematical concept? For example, wheelers. Was it a creative moment of narrative inspiration, or were you thinking about how do we evolve wheels instead of legs?
You got it. That was my friend Jack Cohen and I were doing something for the BBC down in Plymouth, which was a 5-hour drive away, mostly motorway. And we were driving down the motorway, bored out of our tiny minds, and Jack said, let's design a plan for a science fiction novel. He said, I've always wondered whether there is any legitimate way for aliens to evolve wheels. Because biologically it makes no sense. And Jack and I, being the type of people we were, immediately thought, that's a good idea. And if it doesn't make sense biologically, we have to find a way to tweak biology so that it does make sense. And I think I said to Jack, look, couldn't you have what we could have is a kind of symbiosis between fairly legitimate biological creatures. They wouldn't be quite like us, but they would sort of reproduce in the same sort of some sort of genetics, some sort of chemistry. But suppose they were to excrete heavy metals, and over time had evolved the ability to not just excrete them, but to actually turn them into little machines. And then this symbiosis would develop, And the machines, which would have wheels, would get so complicated that they were effectively a life form of their own, except they were kind of piggybacking on the reproduction of the genuine biological aliens. And, oh, yeah, that would be good, he said. Okay. I mean, it's cheating for evolving wheels, but nonetheless, we have wheeled aliens. That's good. Where would these aliens live? Oh, I know, he said. They could be these balloon creatures on Jupiter. Right. And then the whole story evolved rapidly from there. Why does Earth come into contact with the aliens on Jupiter? Because they're throwing a comet at us.
As you do.
As you do. This means they have some sort of gravity control. This is both a threat to the Earth and rather interesting. We better go there. And then, of course, you have to have some sort of tension in the whole thing. So on Earth, there's the official expedition, and then there's the unofficial one, which is the one that solves the problem. And on Jupiter, there is the Jovian equivalent of the government, and there are the rebels. Yeah, and then of course it starts to get complicated, and that gave us our story.
Yeah, the science was easy, the politics was the difficult thing.
That's right, but it was such fun to write. I write these things, and Jack and I wrote these to find out what happens.
Yeah, I was going to ask.
You don't know. I mean, you start with a plan.
Yeah.
You start with a rough. You have to. If you want to publish it, you send them a synopsis. Here's what the story's going to be like. Yeah. And 2 months into the writing, you tear up the plan because your characters start saying things like, sorry, but I wouldn't do that. No, that's not the way it would happen at all. No. It's got to be consistent with what you've been developing. How about, and your characters speak to you.
Yeah.
I wrote a mathematical paper, and this is almost an answer to one of your earlier questions. I wrote a mathematical paper on combinatorics because I'd been writing about some mathematical problem for Scientific American. And the way I wrote the columns was they were a story and there were characters. And this particular story was about the worm family. Okay, so there was daddy worm and mother worm and baby worm, basically. And I got to I was sort of towards the end of writing this column, and basically daddy worm said to me, that can't be a difficult problem to solve. There must be a way to do that. It was about dissecting a rectangle into 3 pieces. And it's only 3 pieces. So my character, I mean, this is certainly what it felt like.
Yeah.
It felt like my worm character said to me, you can solve this. So I sat down and solved it. And then I made the worm a co-author in the published paper.
Wow, can you get away with that?
I got away with it.
The reviewers weren't looking too closely that day.
No, Albert Wormstein.
Oh my God, have they ever caught that? No.
If they did, they saw the joke and decided to go along with it.
Okay. Oh, goodness.
I don't know.
Right.
Journal of Combinatorial Theory, Series A.
I wonder if he's being referenced in works.
Yes, it does Wormstein appear in the citation index?
Yeah, he must do.
He must do. Yes.
Yeah, well, that's my suspicion, actually. Hearing you tell that story, I do wonder if you're using science fiction as a way to solve problems. And with the book Flatterland, which was your sequel to Edward A. Abbott's Flatland, were you just using fiction to just solve some geometry and questions about nature of reality? Or
well, the original Flatland book had 2 parallel objectives.
Right.
One was to explain 4-dimensional geometry to the Victorians, and one was to make social comment about inequality in Victorian society, particularly regarding women.
Right.
So in Flatland, it all lives in a plane, Euclidean plane. The people are polygons, triangles, squares, pentagons. the more sides you've got, the higher up the social ladder you are.
Right.
The priests are circles, which everyone knows are not real circles. They're just polygons with lots and lots and lots and lots of sides.
Right.
The women are lines, humble lines, and they're not very bright. And he did this not because that's what he thought, because he was actually a pioneer. The author, Edwin Abbott, was a pioneer of women's education, really pushing for it. He did it to show up the way the Victorians were treating their women.
Interesting.
But he had this dual objective. So when it was suggested to me I should write a sequel, which was not a new idea, several people had done it, but why not bring it up to date? I had to have the same dual objectives.
Right.
Yeah, I wanted to explain. Okay, so the fourth dimension was interesting to the Victorians because this was the kind of new idea from science that had started to appear. It was obviously very mysterious. There were all sorts. The spiritualists all said, well, of course, the spirits live in the fourth dimension. That explains it all. It's scientific. So there was a lot of interest in it for good or bad reasons.
Right.
Well, the modern analogue would be all of the strange geometries at the frontiers of physics. So I thought, okay, so we have to have a way of going from one geometry to another, one space to another. Now in Flatland, the sphere comes along. He's three-dimensional.
Right.
Yeah, so the analogue is Flatland is two-dimensional and the sphere explains three dimensions to them, and the Victorians can see all this because it's just a plane sitting in space. But then the hidden point is, look, you in your three-dimensional space are like the Flatlanders, and you are having trouble comprehending the fourth dimension.
Right.
But from the point of view of space, you can see that the Flatlanders really shouldn't have worried because it's perfectly obvious what spheres look like.
Right.
So you should be able to understand a four-dimensional sphere.
Okay.
Right. And he doesn't go quite that far, but he uses this dimensional analogy.
Right.
So I had to do the same thing. And in order to address essentially the same problem in today's world, which is the general lower status of women, it made sense that the protagonist of the book should be female.
Right.
And it turns out that only at the end, so she's a line for most of the book. At the end, it turns out the line is actually an edge of a square pointing out into an extra dimension. The females are squares as well. They just point into they have another dimension that the males are lacking.
Right. Oh, that's fantastic.
And then it went from there. And I had to have an analogue of the sphere. What sort of creature can take you from one space to another?
Right.
Well, I realised a space hopper.
Oh, goodness. Well, is there any topic that you would love to explore that you haven't yet? I'm thinking, I know that in Does God Play Dice, your non-fiction book, you've explored chaos theory. You ever thought about playing with chaos theory within sci-fi realms? Or
I've used a little bit of it in sci-fi stories. I use quite a bit of parallel universes, and there's one short story I wrote which is actually to do with evolution. Right. It would take too long to explain it, but it was based on some work in evolutionary biology, which I decided I didn't agree with. So I wrote a story in which things happened contrary to these evolutionary beliefs. To be honest, there are several topics I would like to write about, but there's a lot more competition nowadays, and they tend to get there first. So I was going to do a book on Fermat's last theorem, but then Simon Singh beat me to it, and he'd been involved in a BBC programme about it, so he had all the material at his fingertips as well. So I don't propose a new book to the publisher anymore unless I can find a topic I really want to write about and which no one else is doing. And recently I finally found one. It's not the content, it's the packaging.
Right.
It occurred to me that one of the great driving forces in mathematical research is trying to outdo everybody else.
Right.
You don't just want a theorem, you want the best possible theorem.
Right.
Yes. I mean, the four-colour theorem, which is something people probably heard of, that any map can be coloured with 4 colours so that adjacent regions don't have the same colour.
Mm-hmm.
Well, for a long period, it was known you can definitely do it with 5 colours,
Right.
and nobody can find a map that needs 5. They always work with 4.
Right.
Right. So the person who had the 5-colour proof has got his published theorem, and everyone is trying to improve on that, either by showing that really is the best possible or by showing it's not. Okay, I thought there's a lot of interesting mathematics that can be packaged as mathematicians progressively trying to find better and better and better results, either the same theorem with weaker assumptions or a stronger theorem with the same assumptions.
Right.
And it's not just in the 4-colour theorem, it's all over mathematics. It's a competitive sport.
Right. And this is your next work?
This is the next book.
Right,
yes,
okay.
It's coming up. The working title is Quest for the Best.
Which sounds more like an autobiography. But anyway, the wonderful thing about you, Ian, is you're not just an emeritus professor at the University of Warwick. You're also a wizard of the unseen university. So for any of the uninitiated, what does that mean?
Okay, so this is a big change in my life. One of these life-changing events, it really was when my friend Jack Cohen dragged me off to the Novacon Science Fiction Convention in Birmingham. And we were sitting there in the bar at lunchtime, and somebody wandered in, and Jack said, "Oh, there's Terry." I said, "Who's Terry?" He said, "Terry Pratchett." I said, "Oh, I think I've heard of him. There was an interview in Interzone magazine. He does fantasy stuff." And Jack said, "It's not the same sort of fantasy stuff as everybody else. You should meet him." So he called him over. "Oh, hi, Jack. How are Terry?" They had been friends before Terry was famous because they both went to science fiction conventions. Terry was at this convention as a fan, not as a guest, not as a speaker. He came, he paid his entrance fee for the day to talk to his mates and just generally slob out with the science fiction fans. So we had lunch together, and we discovered the three of us actually all had very similar interests, and that we had things in common and things we didn't have in common, which was great fun. So for years afterwards, every time Jack and I were travelling near where Terry lived, we would go and see him.
Right.
And then at another science fiction convention, we got fed up with the hotel food. So the three of us went off to a Mongolian restaurant in Dudley.
As you do.
As you do. In my brand new sports car, which Terry Pratchett looked at and said, "Mathematicians should not have a car like this."
120 books.
Yeah, we could afford it. Yeah. Anyway, and this was at the time when the book called The Physics of Star Trek was attracting lots of attention. Yeah. And this was a physicist explaining how warp drives and Beam Me Up Scotty and all of this stuff actually wasn't completely impossible in terms of known physics. Right. And we were talking about this, and the idea came up that we ought to do something for Terry Pratchett's fantasy world, which is Discworld. Yep. Which is a flat world supported by 4 giant elephants on the back of a giant turtle that swims through space and inhabited by witches and wizards and trolls and all of these things, and magic really works there.
Right. Okay.
In fact, it's the only thing that really works there. Everything basically works on magic. Okay. So we thought we really ought to do a physics of Star Trek for Discworld, science of Discworld. And Terry said, "Great idea. I'd love to do it. In fact, there's a lot of pressure. I should do something educational with Discworld. And I'd quite like to. But Discworld doesn't run on science. See, it runs on magic. It runs on narrative imperative. Things happen because the story says they must. If you're the 8th son of the 8th son, you must become a wizard. Right. Even if it turns out you're female. And female wizards don't normally get into female students don't get into unseen university to train as wizards. Nonetheless, it has to happen. Right. And he has a whole book based on this. Okay. We said, well, Terry, there's lots of science in Discworld. There's Grebo the cat who is locked in a box, and it turns out there's 3 states for a cat in a box: alive, dead, and absolutely bloody furious.
Very Terry Pratchett.
And he said, no, we can't write a book about that stuff.
Yeah.
So Jack and I went away with the whole thing sort of sitting on the back burner and a challenge. How do we write that sort of book, a popular science book based around Discworld when there's no science in Discworld? Well, it took us 6 months to see the obvious. We were in the common room, maths common room at Warwick, and one of us, and I can't tell you which one of us, said, if there's no science in Discworld, can we persuade Terry to put some there? How do we do this? Because it has to be insulated from the magic.
Right.
Because basically a bit of science in Discworld would disrupt the magic. And conversely. Oh, so there has to be a containment field to keep the science and magic separate. What does it look like? It's football-sized. It's a very powerful magical field that keeps the magic out of its interior. What happens inside it? Round world. Right. Our planet, our universe, everything runs on laws of nature, not on magic. Things don't happen because people want them to. They happen because they want to. The wizards will have kittens thinking about this stuff. Everything inside the round world project is weird. It's all wrong. The worlds are round, not flat, but the people will fall off. Yeah. No, there's a thing called gravity sucks them up onto it. Yes. Weird. That's right. So the running joke is our world is crazy.
Weird to the wizards.
The wizards' world makes perfect sense.
Yeah.
And so we ended up writing 4 books on this.
Whoops.
So we finished The Science of Discworld, and it got to number 2 in the bestsellers and did very well. And Terry said, that was great fun. We can't do another one. So why can't we do another one? He said, it's too much fun and the sequel's never as good. And no, we just can't. And eventually we figured out he didn't mean that. Oh, well, then he said, if we did do another one, what would it be about? We thought, aha, there's the opening. Yeah. It was actually an invitation to me and Jack to devise scenarios which would let Terry do his short story, because the structure of the book wasn't like Physics of Star Trek. The structure was, it's a story about the wizards interacting with Round World, interspersed with long chapters on science explaining what's actually going on inside Round World, what's puzzling the wizards. So it has 2 separate but interwoven components, but one is a Discworld short story. And it turned out that what Terry wanted us to do wasn't to tell him what science would go in. It was to tell him what the story would be like.
Right.
And then inevitably, whenever we got one, he would say, it would be a case, okay, Terry, here's what we think the story should be about. And he'd say, that's close. I'll tell you how it would go. And at that point, so we had to provoke him into writing and designing the story, and then everything would work. And we repeated this technique 3 more times.
Well, it sounds like that's such a, it's a wonderful collaboration. And everything that you've shared with me over the last hour or so, it feels like your career is so diverse, but it's because of all these wonderful collaborations.
Yes. That's absolutely true. There are several other people I've not mentioned. Most of my mathematical research has been, certainly since 1983, when I changed fields, most of that's been done in collaboration with an American mathematician called Marty Golubitzky.
Right.
And Marty and I have dozens and dozens of joint publications, often with other people as well. We still work together. We still meet up over Zoom. We have various projects going on, some of which are actually mathematical biology. I do things on my own, but an awful lot of what I've done is collaborating with other people. You find the right collaborator and it works. Yeah. The collaboration produces things that neither alone could have done.
Right.
Jack and I discovered this quite early on, that when we were having joint discussions in pubs and things, Jack and Ian seemed to know things that neither Jack nor Ian knew.
Or knew they knew.
They knew. Exactly. Bubbling up from the subconscious.
Right.
Yeah. So I've been very fortunate to have a lot of very good collaborators that I get on with well, and some collaborations can be very difficult.
Yeah.
I know one case where the two authors spent all their time fighting over where to put the commas.
Right. Okay.
And each one kept changing what the other one had written. No, you have to converge.
Yeah.
You have to be prepared to compromise a little. But basically, you have to have someone who is a fellow spirit who thinks along similar lines to you, but different enough to make it interesting and bring new ideas into the collaboration.
Well, what would you say is the, I guess, science or perhaps magic of a successful collaboration?
I don't know. It's just it's often the chemistry of the two people as well. Yeah. Usually with these people, you meet them accidentally, and within 10 minutes, it's as if you've known them all your life. You just click.
Yeah.
I met Jack Cohen because he phoned me up about my book, Does God Play Dice? And he wanted to ask some questions. And This was Jack's modus operandi on everything. As a result of which he knew huge numbers of people. Yeah. And he phoned me up, and so I thought I was open to such meetings. A lot of people would say, "Oh, I haven't got time." No, I'll have a chat. Went off to the pub. 4 hours later, we were still in the pub, chatting away. And a week after that, I went over to his house over near Birmingham in Bromsgrove, where he had a llama, a donkey, 5 sheep, 3 dogs, about half a dozen cats, frogs, turtles. He was a biologist who actually was interested in and kept animals.
Did you go, let me tell you how all of those are walking?
Not at that point. That came later. Jack and I wrote a couple of papers on mathematical models of evolution based completely on a remark he made to me in a pub when I was trying to explain my symmetry and dynamics ideas. And there's a thing called symmetry breaking, which is where you have a symmetric system, but the behaviour is less symmetric.
Right.
This makes sense mathematically. And Jack said, speciation, formation of new species. That's like it, isn't it? Because you start with one species, which is very symmetric because all the animals are the same.
Right.
And you end up with 2 species, which is less symmetric because some of them are different. And at the time I said, no, Jack, you're not following what I'm saying.
Right.
And I went away and it started to sink in. And the next time we met, I said, Jack, that was a great idea. I know how we can model that mathematically. And we had our mathematical model of speciation and wrote a couple of papers on it. And it's used as an example in a couple of my mathematics research textbooks.
Yeah. So in many ways, these collaborations, they're mathematical improbabilities.
Yeah, they almost always start with an accidental encounter.
Right.
You meet someone for whatever reason, get chatting, and sparks are struck. It's happened to me about 7 or 8 times over the years. It usually happens about every 5 or 6 years or so.
I feel like there's a mathematical paper on the probability of accidental encounters.
They drive a lot of the interesting work in mathematical research. Yeah.
These moments of inspiration where it strikes. Ian, I have to ask, if there were any aspiring mathematicians or individuals who are passionate about maths and passionate about science fiction, what advice would you have for them?
Okay, I think the important thing is not to get too hung up on the details, the technicalities, the difficult side of mathematics. People like you're talking about probably actually don't have too much trouble with that kind of thing anyway.
Right.
But what I did, and it shows in everything I've done since, when I was in that position in the sixth form at school, about 15 or 16, 17 or 18 for the sixth form, but in the other classes slightly earlier, I went to the local library and I tried to find books on mathematics that were not part of the school syllabus.
Right.
I was looking for things outside it. I was helped in this by Martin Gardner writing his very famous column in Scientific American magazine called Mathematical Games.
Right.
And by my senior sixth form maths master, who was also my form teacher, who took 5 of us out of the class and taught us some maths outside the syllabus in his free periods, on the grounds he knew damn well that we could do everything in the syllabus and knew it already. And in fact, he proved this to the headmaster, and it's why I got to Cambridge, but that's another story. So I realised what was a big secret at the time, which was there's new mathematics all the time, there's new research. A lot of it's fun or can be made fun. Yeah. It's interesting. It's not the sort of, I was quite interested in the school maths, but that was a bit routine and a bit boring in comparison, to the amazing things you would find in Martin Gardner's columns. Like you could make a machine out of lots of matchboxes with something like dried peas inside them, and a little picture of a noughts and crosses board on the top, and you could teach this machine to play noughts and crosses perfectly. Right. So on the top were all the possible positions, right, and the move to the next position, and you played the game, and you randomly chose moves, and if you lost, you put a P inside the matchbox. We're saying, don't use this one.
Don't go this way.
So if you want to make a move, you pick it up and rattle it. And if there's a P inside, then you don't do that. Which means that you have to track back one step to your previous move. Something obviously went wrong there. Yeah. And after a while, this machine, it learns to play noughts and crosses made from matchboxes.
Wow.
Right? Now, things like that, particularly when you're 16 or 17, I made the machine. I trained it.
Really?
Oh, yes, I did the whole thing.
Oh, blimey. Peas and matchboxes. Oh, the times before Netflix. Well, Ian, this is the Futures podcast. So the final question always has to be about the future. And given your background in both science fiction and mathematics, do you have some perhaps predictions for the future of these fields, or do you see any emerging trends or developments that might be worth exploring?
Oh, yes, I think they're all fairly obvious, but we've touched on artificial intelligence. That is going to change a lot of things. The computer side, there's a lot more interaction between maths and computers now. Yeah. There's a lot more interaction between maths and biology. In fact, there's a lot more interaction between maths and the rest of the outside world in all sorts of ways. Warwick now has the Mathematical Sciences building, which is designed for people to do that kind of thing. They should be mathematicians, but they should be collaborating with the local hospital, doctors, with biology department, whatever. Yeah. That trend to interdisciplinary work is growing all the time, and I think very healthy. Yeah. And it inevitably will change to some extent the way mathematics is taught and the way we do it. And I think that's happening already. The computers enhance mathematics in the way that the microscope enhanced biology. Yeah. It didn't make the biologists obsolete. It just opened up a new world. It did mean a lot of what they had been doing suddenly had to change, because once you see what's going on the smaller scales, you realise a lot of what you thought was true is probably nonsense. Yeah. If you know animals are made of cells, then cell biology suddenly becomes a crucial part of how animals work. Yeah. So the computer at the moment is a wonderful tool for mathematicians to use. We can do experiments. I'm doing it at the moment. I'm working on a fifth edition of an algebraic number theory textbook, and calculations in algebraic number theory are really difficult by hand. Right. I'm getting the computer to do it now. But so will the people who are being taught from the book. So it's okay.
Okay.
Yeah. And there are also lots of inputs from mathematics into computer science, because mathematics is the theoretical side of computer science. And as we said earlier, the algorithms that are being used are at root mathematical. So there's this nice two-way trade between maths and computing at the moment. It is certainly possible that if artificial intelligence gets sufficiently smart, it will start taking over the mathematician's job completely. You'll log on to the computer and say, I thought of an interesting theorem today, let me show you the proof. And you think, oh, okay. Yeah. Am I about to become obsolete? I think the human side is going to is not going to be made obsolete, but it would not totally surprise me. I don't think AI at the moment, if you scratch the surface and probe a little deeper, you find all sorts of problems with it, and it's not as clever as it appears to be, and so on. But it's a lot cleverer than people thought it possibly could be. Yeah. Alan Turing saw this coming. Yeah. Ada Lovelace saw this coming back at the time of Charles Babbage and mechanical computers. Yeah. Very few other people saw this coming.
Well, it feels like the only way AI can be a useful collaborator is if you give it access to the mathematics common room at the University of Warwick.
And get it to drink coffee with you.
And get it to drink coffee or perhaps a beer. Ian, it's wonderful to hear that there's so many new worlds for mathematics. And I think, finally, I've understood some maths concepts. I think I actually understood some stuff that we discussed. So that's extremely exciting for me. And Professor Ian Stewart, thank you for being here. Thank you for being a guest on the Futures podcast.
Well, thank you for inviting me. It's been enormous fun. And this is a very worthwhile activity.
Thank you to Ian for showing us the unexpected beauty of mathematics. Ian's latest science fiction novel, Loophole, is available now from Elsewhen Press. You can find out more about the hundreds of books that he's authored by using the links in the show notes. If you like what you've heard, then you can subscribe for our latest episode. Or follow us on Twitter, Facebook, or Instagram @Futures Podcast. More episodes, transcripts, and show notes can be found at futurespodcast.net. Thank you for listening to the Futures Podcast.